Okay, we're live. Thank you everyone for joining us today. Welcome to our webinar, Resilient and Sustainable New Concrete Solution for Offshore Renewable Energy. We are delighted to have you here. And today you will learn more about two European funded projects that are NATURSEA-PV and SureWave project. But you will also know more about cutting-edge innovations, about high-performance concrete and geopolymers. So, as you know, these cutting-edge innovations are not only improving the durability of shore structures, but are also doing something very good in reducing the environmental footprint. Without further ado, I would leave the word to our first speaker, Edurne. I don't know if you can share your screen. Yes.
Yeah. Good morning. Can you see my screen?
Yes, we can see it.
Okay, let's see. Is it now in
yes, it's
presentation?
In full screen mode. Yes.
Okay.
Yes.
Well, welcome everybody to our first NATURSEA-PV webinar. In this occasion, we also have our sister project SureWave with us. And okay, let's see if I can move the slides. Yes. So basically what we are going to do is like a short introduction of both projects, NATURSEA-PV and SureWave. And then we will concentrate more in two talks in the development of concrete solutions that we are carrying out in the SureWave project and also in NATURSEA-PV. So both projects are within the context of the European Green Deal. As you know, Europe's ambition is to become the first climate neutral continent by 2050, with the objective to be for the green transition to be beneficial for citizens and businesses. And renewable energies play a key role in the green transition, as you know. However, most renewable energies require large areas for gigabyte scale electricity generation, and so placing them on the water seems like a smart solution. But offshore floating photovoltaics is still in the early R&D stages, and so these two projects try to bring this offshore floating photovoltaics to reality. So this is the context of both projects. So in the case of NATURSEA-PV, the strategic objective of NATURSEA is to improve the overall lifetime, reliability and maintainability of marine substructures for offshore floating PV to reduce degradation and failure rates, and thus investment risk and levelized cost of electricity. So basically we have a design of the substructure for photovoltaics, which we based it in nature, basically in a water lily. And we have, we started in that with that design, and we have evolved that design to obtain a substructure that can withstand the extreme conditions of the offshore environment, of the sea environment. We wanted to develop materials for that substructure based in concrete, specifically in ultra high performance concrete. But we want to make it more sustainable. So we're working with low clinker cements and geopolymers. And we are also developing coatings for using bio-based monomers. Instead of coming from petrol, it comes from biomass, and to reduce biofouling in that substructure. We are also working on developing new predictive computational toolkit to predict durability of these materials and elements, and therefore do maintenance planning. So we are working in developing microstructural model of the matrix, also modeling surface treatments, multipath transport model and mechanical model, and to combine all of those to get the predictive computational toolkit, and then do durability predictions and maintenance. We want to test our solutions in realistic conditions. And in fact, the design that we've done for the substructure was tested in the basin test by Marin. And I'm showing here one of the tests it was carried out. This was quite an interesting test and trip we did to see these installations. It's amazing. So as you can see there, it's the design, and the waves are coming and they are taking the measurements. We also recently put specimens, ultra high performance concrete developed in the project, and coatings as well in the harsh lab platform that Tecnalia has off coast of Biscay. And they're going to be there 6-8 months, and then we'll take them back to the lab and we'll do some characterizations for chloride, fouling, and sulfate attack. And then later in the project, we're also going to produce different components, the prototype components like beams and a floater, and put it off the coast of Galicia and also of the Basque Country, Mutriku, and then analyze a little bit what happens with those elements. Besides the objectives of the designing of the substructure and the development of the sustainable materials, we are also assessing environmental and socioeconomic impacts that this deployment of this photovoltaic offshore platform might have in the sea environment, also in society, for society, and also important stakeholders that live off the sea. We are also assessing regulatory constraints to deploy this substructure. And we also want to enhance social perception by means of workshop organizations, courses, webinars, networking with clusters, and so on. We are a multidisciplinary team. We are 11 partners from different countries in Europe. And we still have 1.5 years to go, more or less. And basically, this is my talk. I may be a little bit too fast, but I'm open to any questions you may have. Thank you.
Thank you very much, Edurne. So for now, we do not have questions. So we can proceed with the next speaker, Balram.
Yes.
He will give us an introduction to the other European funded project that is here with us today. That's SureWave project. So Balram, the stage is yours. Thank you.
Yeah, thank you very much. Do you see my screen?
Yes.
Yes, then I'll just take a laser point. Thank you very much, Claudio and Edwin, for this introduction for SureWave. So as it was mentioned that both NATURSEA-PV project and SureWave are like kind of sister project. They are basically addressing the same challenge, like designing the floating FPV solution for extreme offshore environment. So with this, I will just start a little bit background actually. What are the key technical challenges actually? So as you know that most of the FPV solutions, when it comes to the onshore, mainly in the lakes and the dams, they are at high TRL. The reason is that normally you see they're not very extreme environmental condition when it comes to the wind and when it comes to the waves. But when you move on from this onshore to the offshore condition, things become completely catastrophic actually. What happens actually, you have extreme high wind speed, you can have extreme waves actually, and on top of that you have current actually. So what will happen actually, basically this will lead to the fatigues in the joints and the connections, and these are the weakest component for any offshore structure. So another problem, as was mentioned, that it was a saltwater corrosion, which you don't see in the freshwater lakes, which onshore PV are today are matured. You have the biofouling, and then this constant movement of these PV modules or other component could result in the micro cracking and de-alignment, which can basically kill the entire project. And on top of that is the low maturity technologies available, and they are not well defined design standards and guidelines and legal regulations. So in order to address some of these key challenges, there was a call from Horizon Europe, and the call was that we should design a FPV system which can withstand the wind of 25 meter per second, wave of 14 meter high, and the current of 1.25 meter per second. And at the same time, when you introduce or design a new material, that should be more or less 100% circular. So they are a very, this is a very ambitious goal to achieve. But then both NATURSEA project and Shoreway took the challenge. And then on the top of that, basically we want to improve the service life. And when you do this sustainability assessment of the concept, we want to make sure that we have reduced CO2 footprint, we have improved marine life. At the same time, we should able to reduce the levelized cost of energy production. So these are the key challenges that we need to address. So in Shoreway, actually, the key objective was that we want to develop and design an innovative concept of FPV, which basically consists of an external breakwater, and that should be made of new circular material. And this should allow an increased operational availability and the energy output. So this shows you the overall idea of the Shoreway project. So what you see is FPV concept, which is provided by our project partner Sunlight Sea. So the beauty of this concept is that it is made with the aluminum actually, which is marine grade aluminum. So you don't have any problem with the corrosion actually. The only challenge what we have actually, could be subjected to the extremes wave condition and wind condition. So what we did in this project actually, we introduced a breakwater. The goal of this breakwater basically to attenuate high frequency waves, which are very dangerous to the FPV system. And basically our goal is not to basically eliminate or attenuate high frequency wave, because under the high frequency, the entire system will flow through. So it's not a problem for the structurally, the low frequent waves are not the problem, but the high frequent waves are the problems actually. And that is what we want to address through the Shoreway project. So for that one, we have made some quick video maybe, which I've just run through this video. So this was basically a global concept of the Shoreway project. And in this project, we are a 7 partner, both from industry and research from 4 European countries. And this project was started in 2022 along with the NATURSEA-PV project. So what are the key objective or sub-objective in this project? The first objective, basically, we want to design this novel floating breakwater actually. And the goal of this breakwater it should protect and attenuate this wind, wave, and current, which are harmful to the internal FPV elements. And at the same time, we want to create a coupling between these external breakwater and internal FPV. And for that, we were working on this innovative mechanical joints design. And we want to also optimize the anchoring and mooring of the complete FPV system. And basically, we also want to address the layout optimization. So layout means like, how do you place your breakwater? Whether it should be circular, it should be square, or any other shape. So that is something we have been addressing through Shoreway project. So the first thing first. So first, our goal was to design a breakwater. So for that, our project partner Clement, they have been working with various design parameters when it comes to the breakwater. That includes the width, length, height, weight. So many parameters were considered when it comes to the designing this breakwater. And the goal was that how close or how far we can reduce this low frequent waves, high frequent waves. So that was the goal. So once we designed this breakwater, our next target was that how to place these breakwaters, like number of breakwaters, the shapes like circular, polygon, triangular, oval. So what was done actually in this project, actually, we made a matrix and we chose different parameters. And in this one, we gave like rank 1 means highest ranking and rank 5 is lowest ranking here. So after doing couple of iteration design optimization, we found that in our case, circular layout is the best one. So once we are done with respect to selection of the breakwater, selection with layout, then our next target was that what material should be used. So I'm not covering this objective. Our project partner Akuna, while I will present in her next talk about the circular material. So I will not cover this objective. I will just pass through this slide. And then as we have the common objective in both NATURSEA-PV project and Shoreway, basically coming with a new predictive computational tool. And as you know that doing the experiments are very expensive, and this is a multidisciplinary problem. So we have to design a bunch of softwares and bunch of code. So one of the key challenge was to design high fidelity coupled arrow hydrodynamic simulations. So this is done together with the Marine, which is a common partner in both the project, and we have these tools available now. And you know, this concrete is a complex combination of various raw material. And basically, if you want to design a concrete, you have to run through various lab experiment, and you want to avoid that one because two reasons. One is expensive, second is a time consuming. So Syntep has developed this machine learning algorithm, basically which takes into account various input variable, combination of various raw material, and you can basically find out the complete or optimum mix in such a way you can get the good or improved structural properties of the concrete. And then, you know, when you're designing the material, the challenge comes how to assess the structural integrity, like considering the extreme load, hydrodynamic load, wind load coming. So we have been working with the advanced FE model to basically assess the structural life of the component. But we have the challenge. These structural like FEM models are computationally demanding. So then we came with making a simple or faster model. And these models we keep in the category of called structural health management system. So these models are designed in such a way that you can use this model to predict the lifetime of the component also. So these are based on the machine learning, running the advanced FE simulations, gathering the literature data. So one of the goal maybe in the next webinar, we will organize together both NATURSEA-PV project and Shoreway will have joint workshop webinar where we'll discuss on this numerical tools. So we'll discuss in detail. And since even though, you know, it's a TRL5 project, but we need to validate our concept at least at the TRL5. So first thing, as I mentioned that for any offshore structure, one of the key challenges is the connection system. So this connection system need to withstand the static load as well as fatigue load actually. So Syntep has advanced testing lab where already we have done quite many rigorous experiment to assess the structural behavior of the connection system. And thankfully, actually, with the help of our colleague at Syntep, we are able to redesign a new connection system, which was able to withstand, which is the connection between the two PV panels. And then for hydrodynamic assessment performance, again, we have joint partner Marine, which is basically doing this 1:20 scale. Basically, I will show in the next slide, actually, not the video, but the picture. And for the long, so this was like connection system. Then we move on to the complete one scale, our complete model testing. And at the same time, since we are developing this new circular material, we need to do at least some long-term degradation assessment. So that is planned in June, July. So we'll be having one breakwater, which my colleague, my partner will present in our next presentation. So I will not cover this topic also here. This actually what we are doing, actually, we are analyzing the connections between the breakwaters and the PV and other connection system. And this picture is taken from marine, actually. So we have done so far two assessment, hydrodynamic assessment. One is one was with and without breakwater, and then we had one standard connection system, and then we are modified. So these data are also available. If you need, if you want to validate your hydrodynamic model, you can approach us. We can provide you the data, and you can use this model. So, okay, so this I'm not going because I'm also already used my time, but I can just some take key aways from the Shore project, actually. So we have this floating PV solution, which should able to work in the extreme offshore environment. Our concept is based on the breakwater, which is made of this circular and sustainable material. And we try to use machine learning based approach, not only for the predicting the concrete property, but also to use the structural health monitoring system, utilizing the advanced high fidelity finite element simulation results. And we have done multiple testing in order to make sure that our concept has achieved the TRL5, like lab testing for connection system, hydrodynamic assessment. We already finished 2 tested, and we have done a lot of concrete lab testing. And then we have soon this concrete prototype is coming. And again, as Adrian was mentioning about this integrated assessment. So we also have same goal, because once you are introducing a new design or new materials, you want to make sure that it doesn't affect the environment. Our innovation should basically climate positive, like with a reduced CO2 footprint and improved marine life. So that will be also, and that is what we are focusing current in the project, actually trying to assess the marine life and all biofouling, everything we are doing at the current stage of the project. So with this, I would like to thank you, all of you, for listening this project. So yeah, thanks. Yeah, I'm open for the discussions or questions. So please.
Thank you very much, Balram. Obviously, attendees have all the time to think to questions and answer them. We will answer them at the end, or at the end of each of the remaining 2 speeches. So we can go on with Valle. I don't know if you're ready. Valle will tell us about the development of concrete solution in the ShoreWave project. So, Valle.
Can you see my screen?
Not yet.
All right.
All right, now we can see. Yes. The stage is yours. Thank you.
Thank you. Well, I'm going to talk about the concrete developed within ShoreWave project about new circular material solutions. Introduction, the points I'm going to talk are objectives, design of circular high performance concrete, circular lightweight aggregate concrete, and circular cellular concrete. Also, durability assessment of the optimal circular concrete solutions, and floating concrete breakwater prototyping. Well, the objectives within ShoreWave project was design a new circular concrete solution for the structural cell of the breakwater. And on the other hand, new circular concrete solution for the inner of the breakwater. And the life objective has been design and prototyping of the floating water. Well, for circular concrete for the structural cell, there are two types of concrete tested. They are high performance concrete and lightweight aggregate concrete instead of conventional concrete. And then for inner concrete of the structural breakwater, the new concrete will be cellular concrete instead of EPS. In order to scale the demonstration and to design the prototype, the following structure was carried out to analyze the three types of the concrete. It was selected lightweight concrete for top of slab for the mosaic, and for bottom and walls with high performance concrete, and for the core of the structure, cellular concrete. Also with some blocks of EPS. Okay. Regarding high performance concrete, the set requirements were 120 megapascal at 28 days, the density as conventional concrete, and consistency was minimum class F4. In this case, the principal objective in this type of concrete was to reduce the amount of cement by using other products like GGBS, ground granulate blast furnace slag, and fly ash type F in this case. And we got to reduce 22% by weight of the cement. It's a picture of consistency. The consistency was measured through flow-table tests, and in this, the optimized dosage was more fluid than reference high-performance concrete. The circularity calculated was 4%. Regarding compressive strength, the same results were achieved at 28 days. Then sample 2.1 is the same as sample 2 by adding a new admixture anti-corrosion in order to improve the durability. It's a waterproofing additive, and it has been designed to waterproof concrete and increase its durability. Results, technical requirements were met in this case. I'm going to explain the next new circular concrete is a lightweight aggregate concrete. In this case, the set requirements were 45 megapascal at 28 days of compressive strength, and density from 1,400 to 1,900 kilograms per cubic meter. In this case, the target was to replace natural aggregates by recycled or artificial aggregates For example, we recycle aggregates for construction demolition waste, also black steel slabs, and lightweight aggregate from recycled glass, in this case, to replace expanding clay, conventional expanding clay. Well, in this case, 18 doses were tested and analyzed, and the most sustainable and optimized dosage was the 18, where it was used construction demolition waste and recycled glass with cement type 3. Okay. These are samples of consistency. The best consistency, more fluid, it was in this case using 100% of recycled glass, replacing total expanding clays, and replacing 20% by weight by coarse natural aggregates. Regarding concrete strengths, from 14 to 18 doses, they are with recycled glass aggregates, and compressive strength were achieved in all cases. In the same, in this type of concrete also will added in the optimized dosage a new admixture anti-corrosion to improve the durability. And the results obtained compressive strength, density, and a high circularity was obtained in this case. Technical requirements were met with this type of concrete also. The last concrete developed, in this case for inner core of the concrete, was cellular concrete. The requirement, there wasn't any requirement about compressive strength, but density was a high challenge, 300 kilograms per cubic meter. In this type of concrete, 26 doses were needed to optimize the cellular concrete. In the first samples, the materials used are material used in the autoclave aerated concrete. From sample from sample 1 to sample 9, aggregates used are natural aggregates and expanding clay. But result of density were poor. In the next tested or doses, were used recycled glass aggregates. They are lightweight aggregates, and the results of density were improved, and circularity also, until 26. 26, it was made with recycled glass aggregates of the type or proportions or size. And the final circularity was 73. Regarding results, we got to achieve 365 kilograms per cubic meter at 28 days. In conclusion, I couldn't get 300 of density, but it was a challenge. In conclusion, there are the three types of concrete developed within SUREWAVE project. Lightweight and high performance circular for cell of the structure breakwater, and for the inner structure cellular concrete. With the optimized doses, durability assessment was carried out through water penetration resistance tests and chloride penetration resistance. The dosage analysis were high performance with anti-corrosion admixture, lightweight aggregate concrete with FEM type 1, with SEM type 1 with anti-corrosion admixture, with SEM type 3, and with anti-corrosion admixture. There are results. In general, all the circular concrete solution developed for the cell of the breakwater exhibit excellent durability properties on water and chloride resistance. In special, water penetration resistance improves the lightweight aggregate concrete made of anti-corrosion additives. Regarding this work, only I'm going to about manufacturing of the specimen and to measure interface of the cell and inner core carried out by SINTEF. The process for manufacturing this specimen was first make cellular concrete, and then make high performance concrete for the cell. After 24 hours, the molding specimens and cure at 120 grades for 5 hours. This first configuration to analyze interface of cell and inner core. This type first configuration was high performance concrete plus cellular concrete, but sorry, is the example to understand the inner and cell of the specimens. The second configuration analyzed by SINTEF was lightweight aggregate concrete for cell and cellular concrete for inner core. The same way before. Okay. Regarding the prototype, the steel and formwork final position, ready to cast the walls and bottom slab with high performance concrete. The process of the manufacturing of the prototype was casting of bottom slab and lateral walls. There are several pictures. We rented a self-concrete mixer lorry. Materials were loaded through a hopper, and concrete was poured first into the cube and then into the prototypes. Here also, batching and putting in the framework. The concrete was vibrated with this. Then the framework was demolding, and the next step was inner core casting with cellular concrete. In the same cellular concrete were produced on on-site self-concrete mixer lorry. Concrete was poured directly into the demo and then was sprayed, timed, and leveled. The following step was manufactured to the top slab casting with lightweight aggregate concrete. First, top slab reinforcement, application of adhesive for bonding hardened high-performance concrete and fresh lightweight aggregate concrete. Batching and pouring lightweight concrete, vibrating. The process of lightweight aggregate concrete, pouring, vibrating, and the final step was visual, the molding and visual inspection. Prototype manufactured and lifted for inspection. And it's all of my part.
All right. Thank you very much, Valle. I still do not see any question for you. So I think we can proceed with Nadia. Nadia will talk us about the development of high-performance concrete with geopolymers in the NATURSEA-PV project, obviously. So Nadia, when you're ready to share your screen, please do.
Yes, thank you. Do you see my screen?
Yes.
Okay, presentation mode, is it good?
Not really, no. It freezed.
It's not presentation.
No.
Mode?
Not in presentation mode, no. I saw that you clicked on presentation mode, but it actually didn't show up for us.
Okay, I will try again. And now?
Let's try. Nope.
No?
Not yet. Not yet. Not in presentation mode, but you can. We have two ways. You can send the presentation to me, or you can present like this, and we can see.
Okay. Okay, I'll present like this. I hope slides will move. Do you see my?
No, because you have to exit full presentation mode. Yes. Now, if you
Now,
change
if
slide,
I go
we can
to
see.
the second
Yes.
one, yes. Okay.
Yes.
Oh.
Thank you.
So okay. Thank you, Edurne. Thank you, Claudio, for introduction and also for organizing this webinar. I will talk about ultra high performance geopolymer concrete, a solution which is alternative to what was presented before. I am presenting work with a PhD student, which is Youssef Sleiman, and a colleague, which is who is Mehdi Spartai. I'll talk especially about what Edurne described in the beginnings. So I'm involved, or the work I'll present now is involved in the work package 2 and work package 4 for the NATURSEA-PV project, and this is about optimization of the new circular material, and also the validation or the durability material tests of the material developed materials. Our goal is to manufacture supports for offshore photovoltaic panels, and in order to replace high density polyethylene panels offshore. I will present the context or objectives, and the optimization, how we optimized our mixes, because yeah, like the former presentation, the last presentation, we did a lot of mixes before having something which is good. And results about characterization, durability, and some concluding remarks. First, I'll just specify that UHPC, for people who are not aware about this, are used in rehabilitation, accelerated bridge construction, and the material has a projected, this is the most important, one of most important things, about 100-year lifespan. We have a very high strength, durability, and longevity. We are speaking about compressive strength, for example, of at least 130, which is very high compared to concrete, an ordinary concrete. We try, or qualities are usually very good durability, improved resiliency, or external usage life, minimum interruption. Many qualities are given by using an ultra high performance concrete. We have also composition which is not standard, but traditional UHPC is containing Portland cement, fine sand, usually silica fume, water, or water reducer, and sometimes steel fibers. What is important, what is to notice, is that Portland cement is accounting for 8% globally for emission of CO2. So the goal is to reduce this content of Portland cement. This is one of our points, or our aims in this work. A brief state of the art gives some CO2 emission for about 40 mixes of geopolymer concrete, which is the alternative we want to put, with replacing cement with geopolymer process, or other geopolymer process for this presentation. So instead of ordinary Portland cement, we have some gain of CO2, but we can do more. We can do better than this. The goal is to or the methodology is to add byproducts and find the gain of CO2 emission, and obviously, we don't have to produce something which is very high cost. So economical cost is counting also in this optimization. What is geopolymerization principle? To have or to develop or to change from cement using and reuse industrial byproducts, as I said, and reduce CO2 emission. We need to go to this geopolymerization. We are trying to do this in this project, and we can describe quickly what is polymerization principle. It's alkaline reactives that we add to precursors. This is two important elements we have in the polymerization process. The precursor and alkaline give dissolution of silice and alumine, and this alumine and silice goes in monomers, which are restructured and giving a network with aluminosilicates. And after polydecondensation, we obtain that geopolymer that which is strong and which is mechanically strong. Yes, it's a high strength mechanical or compressive, at least compressive strength. In our work, we try to formulate so with the two parameters, or we will discuss these two parameters about alkali reactive preparation and also mixture with precursors. So for our case, we used sodium silicate and sodium or potassium hydroxide. We need to respect some ratios. I don't go into these details because it's something changing according to the whole formulation. We need also to use precursors like furnace slag, silica fume, and fly ash, which are working with that reactive. And we need also to respect a ratio with reactive and precursor. This is the methodology or the principle or how we did our mixes. Our objectives or our specification of the project is about workability and strength, and we need to respect this few points, not more or not less to 18 centimeters diameter for workability. For this, the same test was developed or was shown before, and we need an open time of using this mixture of 20 minutes at least. We need also something about strength compressive. 65 out of 24 hours and more than 130 megapascal at 28 days. So the optimization used that we tried was on these parameters or on these points. We have precursors, we have reactives, and water to binder ratio. Also, it's important for all concretes, and it's important for geopolymer ultra high performance concrete also, because it's when you have the more you have water, the less is your is the strength or the compressive strength. So we need to minimize water in the mixes. So with precursor, I will not give, it's confidential as in the previous presentation, I will not give quantities, but we changed for our mixes, the GGBS fly ash and the slag. The first one is slag, fly ash, silica fume added to sand, fine sand, and this is the first part we tried. And so in the second one, we worked with reactives, and in all this work, we had something which is a reference mix, which is done with cement. So this is our reference. We compare all our results to this reference, which is the same one given according our partners in the project and companies especially. One point important here, we can see that reactives depends, like here sodium silicate, depends on the supplier or when you buy this, because composition can be very different, and you can have different results with different kinds of sodium silicate. It's not something which is standard, or you can buy it and work with it. It can be different from one supplier to another. So we tested a lot of them, many of them, and we tested them with precursors, with different precursors. I go to changing or about reactive. I stay on this point. We used we use usually specimen of 416 centimeters, cubic centimeters, and we see what is happening with the sodium silicate. And we tried also in this results, we tried also potassium silicate, because it's giving more interesting results. The criteria is also always flowability and compressive standards, and this allow us to choose some mixes in that kind of set of tests. And as you see, we are not far from our target, our goal. The 1 day and the 28 days are quite close to what we decided, or what we are trying to find. We have another parameter, or something we work on it, is steel fibers. Here we have two. I will not go into all details. Also, I'm just I can just mention that we use new steel fibers, and also recycled steel fibers, and that lead, or that allow us to have results like for flowability and compressive strength. We know, or we all we obtained a decrease of flowability with fibers, which is expected result, and fibers enhance the flexural strength and also the compressive strength for all mixes. So we can go to, we worked with the new and recycled, and we could substitute about 60% flexofiber, which are recycled fibers, and this gives us the best compromise mix with the 60% flexofiber. So we use recycled materials as many as we can. Some characterization of that mixes. Many tools, many devices in IDESEM in University of Bordeaux are used here. Something usual, which is calorimetry, which can just show the difference here between it's about heat. We can temperature we can register during hydration. During first hours of hydration, we can see that geopolymer shows a lot of temperature is higher in the first hours compared to the reference one with cement, which hydration reactions are delayed a little bit compared to geopolymer. We have also measurement with the ultrasonic pulse velocity in the first days, and we can see that in the first part from 0 to 2 or 3 days, we have what we can find here with that high temperature. If geopolymer is geopolymer hydration reactions are rapid, are happening in the beginning of the process. We have also a high velocity observed in here, and after we have the plateau when all for reference, and geo with and without fibers for this example. We have also tests with electrical resistivity, which which were done for 1 or first day and 7 days. That resistivity can, or that measurement resistivity can show that geopolymer mixes contain aluminosilicate materials, which are activated by alkali solution, that result in more conductive matrix and compared to the cementous blender, and this is why we see less. All the curve here for geo are less resistivity. This is the measurement of resistivity, which is the opposite of conductivity. So the material, the obtained materials are very conductive, and so resistivity is very very low in geopolymer mixes. Other measurement like water porosity, we are with the standards, not usual standards, we are about 12, from 5 to 12% porosity by water. We also did the gas permeability, which is complementary to transfer properties of the geopolymer, ultra high performance geopolymer, and we could measure some values for geo without fiber and with fiber about minus 13 for intrinsic permeability square meters, which are usual values, and so we can just show this. We can verify that we have good values, expected values. We also they are higher a little bit compared to reference, but or cement ultra high performance concrete, but there are explanation of this, and at the end properties are good enough for the application we are targeting. We also work with the acoustic emission. We have a good test, an original test with flexural and emission, acoustic emission during the test, and we can see that fibers we did this for geo with and without fibers. We can see that we can see the brittle failure for mixes without fibers, and the opposite ductile failure for when we add fibers. So fibers are this role to provide the ductile behavior to our concrete, and we can see the activity or the emission which is correlated. The acoustic emission, the noise, like we see here, the hits, and we can see that they are correlated to this failure, and we can predict failure with this increasing of hits also. Like you see in here, when the failure is coming, we can see the emission is very, very high. The hits are very high. Acoustic emission was also done with compressive tests. We have the device here, so we have the gauge here, as you can see, and we applied cyclic compressive strength test on specimen of 448 centimeter cubic centimeters, and cycles are from 20 to 120 megapascal, and electrical resistivity measurements are taken within the ongoing tests. We can show some results. We can see that for the initial cycles we have a low activity, emission acoustic emission activity, and the material is still inelastic. We can see that this is the elastic part, this elastic behavior, with minimal internal damage, almost no damage, and the mid stage between 400 and 800 second, which is a gradual increase in emission in hits, and this is suggesting some micro cracks formation and early damage. And we have later cycles which are increasing with activity of acoustic emission is increasing rapidly, and this is and force level is higher also. That means we have a crack growth and plastic deformation, which is observed which is occurring in the sample. Or you can also talk about damage accumulation and fatigue accumulation with this tests or cyclic tests. And at the end, we have a sharp increase, what we see here, and we have the damage evolution or failure, in fact, of the specimen. We can see the same thing with also the energy, which is given the same indications. It's only indicate it's the spikes occur at the peak of force cycles. If you see that red peaks, and that show crack growth in the sample at high stress level. Now I move to durability tests. In fact, we started the durability test, but as it's not very old test, it's only more than about 2 months. We are now not seeing real degradation of our specimen, but we are doing standard tests like acid attack, like also acid attack and sulfate attack, following the standards, sulfate attack, and also magnesium sulfate attack, which is magnesium attack, which is the third one. We are following the mass and the dimensions of the sample, but also non-destructive tests. We are working all the time with this, trying to have acoustic emission or at least electrical impedance measurement after periods in baths and degrading conditions. So we are also now starting the acid or the climatic chamber tests with the acid fog or spray, because we are doing this because the concrete we are developing will be not immersed, not also not immersed. All surfaces will not be immersed. So we have surfaces in water and surfaces only in saturated environment. So we are simulating this with the exposition of samples in climatic chamber with this salt fog or acid fog, and all that samples are followed, as I said before, with destructive tests and non-destructive tests. So we do flexure and compressive tests, and also transfer and no electrical or acoustic emission tests. At the last time is running. I almost finished. We have also Durni showed that harsh lab photos, and I think last week or 2 weeks before, we could put our samples in what you see here in the harsh lab. We sent them to Technalia, and they could put them in the harsh lab. So we will keep them there about 6 or 8 months till October, I think, at least, and samples can this is not our samples, but we'll have this kind of shape before after, and that the same tests I described before will be run on this samples after this exposition in the Harsh lab. Some concluding remarks, and I finished. We could optimize. You can say that now we have a mixed design which is finished. The targets or the values we were expecting or was searching are obtained. Durability tests are conducted, and all this in lab scale and also in harsh environment, as I said, and all that ensure the self-sensing capability of the UHPC we are developing, because our, as I said in the first test, electrical resistivity and conduction is very high. Because of the component of the geopolymer, and so we have something which is smart, which can be defined as smart concrete, as proven by these tests. We are running, or we run, but I have just some preliminary tests in fire, in a condition of fire. At least 3 hours at 800. We have an oven to expose our samples, and we will follow the mass loss and the compressive strength, and also the reduction of flexural strength after exposition to these high temperatures. So thank you for your attention, and if you have questions, I will be happy to answer. Thank you.
All right. Thank you, Nadia. Actually, we have questions. So we have a couple of questions for Valle from Peter Buitlar. So first question for Valle. Why traditional steel reinforcement is used instead of, for example, basalt reinforcement? And this is the first question. The second question is, why didn't you obtain a durable bonding between the outer UHPC lining and the light concrete inner filing by structure and or anchors? If you want, we can go with the first, and then I will read again the second if you want.
The first question, I think
was, yes. Why traditional steel reinforcement is used instead of basalt reinforcement?
No, and the reinforcement used was conventional reinforcement. I don't know. The basalt reinforcement. My colleague Rafa is here. And the engineer was design the reinforcement and the prototype. I developed the concrete. I don't know if Rafa can speak.
I can search for him. Let me look at the position.
Maybe basalt could improve the durability. Tell me, but I don't know if he means basalt as aggregate or reinforcement.
Sorry. Yeah, they allow me to speak. Yeah, so actually we only focused on the on research on the concrete. So actually, as it was mentioned, the basalt could improve the durability and also the overall structure, but it was decided that only the concrete was gonna be modified with this new type of concrete, and the steel was left like a conventional one. So basically that's it. Yeah, but there are different type of reinforcement. For example, like composite or other, which could improve also the durability of the breakwater.
All right, then there was the second question. Why didn't you obtain a durable bonding between the outer UHPC lining and the light concrete inner filing by structure and or anchors?
And can you write your question? But I don't understand well, I think, the question, the field.
Yes, I can. You can check it in the Q&A section if you want, Valle or Rafael.
Yeah, I
I
think
can also.
I'm reading it. Yeah,
Okay.
I think it's more of a mechanical question, Valle. So I think I can answer, but I think the question is, as I understand it, about the strength between the HPC and the inner material. I will say that the inner material is more of a filler one, and actually, as if we wanted to substitute the EPS, we didn't talk about providing any additional reinforcement, steel or other, to create bond between those two materials. Okay.
Yes.
Actually, the material itself of the HPC is enough to sustain the stresses, and providing additional steel will make the whole floating element weight more. So actually, it was tried to minimize it. Okay.
All right, thank you. We have another question for you. Have you from Achutha? Have you measured the shrinkage of the cellular concrete?
No, shrinkage was measured on lightweight aggregate concrete, but cellular concrete no, because it's a very lightweight concrete. Shrinkage is, I think, is more interesting in studying on high sorry and high performance concrete or lightweight aggregate concrete.
All right, thank you. Then we have an important question, I think, for Nadia, always from Peter Butler. So microsilica, fly ash, and steel slag are all byproducts of the not so green industry. This industry can also disappear in the near future like coal-fired power plants, making your final product less green. Why not using wide available materials as ultrafine fillers like clay or recycled materials?
I'm not sure. It's not that green. It's metallic. Yeah, it's some industries, old industries, and we have to do something with that product. Our life cycle analysis, we did it not on ultra high performance concrete, but on another concrete in here in my team with my PhDs is not that bad, and we have a reduction sometimes about 60% emission of CO2 with the CIMA Pro and the software usually used in life cycle analysis. So we cannot. I'm not sure the mixture is less green. I'm not sure of this, but compared to cement, because that byproducts are here. This is the point. They are byproducts. So the value or the importance is to use them because we don't produce them especially for this application. They are just here, and we have to do something with them. This is why the analysis gives something which is not that bad. With the clays, I work with clays for other applications, but we cannot. We use the metakaolin in particular. which is heated a little bit. Also, it's a clay with the energy, so we obtain good results, but maybe not for ultra high performance concrete. I did it for ordinary, let's say, or for conventional concretes. I know that I love clay. This is my first specialty in research, but it's not always easy to use it in for mechanical performances. And shrinkage. There is a problem with shrinkage also, a lot of shrinkage.
All right. Thank you very much. So we have finished, but before you all go, I have to show you something, because we're, as you can see, we are also organizing an industrial workshop on the 28th of May. And there's also a surprise, because Peter Buitelaar, who actually made some questions in this webinar, will be also one of the speakers in this industrial workshop. So take a screenshot of this, and the registrations are open. You can find them. You can find the right section, the right webpage on our website. Here, as you can see, I pointed out, there's a dedicated position in the menu. So just click there and look at the program. And if you like it, please register and keep following us on our social media for more insights and more information about it. So if there are no other questions, I don't see other questions. It has been a fruitful and happening and event. So thank you very much to everyone for participating. And also one last thing, we will also share a recording of this webinar if you're interested in the coming days. So please keep following us on our social media or on the website. Thank you very much.